Okay, I want to change gears and talk about impossibility of quantum bit commitment. What is bit commitment? We'll talk about a physical analogy. I like physical analogies. Alice has a bit, and she inserts it into a safe. So she inserts the bit B into a safe. She closes the safe and sends the entire safe to Bob. So presumably there's a combination to this safe. She keeps that secret. She sends this device to Bob. That's called the commit stage. Sorry, I had a problem with my animation here, so assume that this is not there right now. Bob receives the safe, and it's now guaranteed. So he holds this safe. So first of all, Alice can't modify the bit B. She's entered it, like maybe on a piece of paper, into the safe, and he has the safe, so therefore she can't modify the bit B. That's called the binding property. And Bob cannot read the bit B right now. The safe is closed, and that's called the concealing property. At a later stage, called the reveal stage, Alice is going to reveal the combination to the safe. So she tells Bob, hey, if you do this certain combination, you will be able to open it. Bob receives that combination and opens the safe, and hence the reveal safe stage. That is bit commitment in a nutshell, and the importance of bit commitment is in that, first of all, early work showed that quantumly, if we have a bit commitment, then we can actually build what's called oblivious transfer. Oblivious transfer in itself is known to be universal for multi-party computation. So it's a building block. I'm not going to describe actually oblivious transfer, OT. It's almost as cleanly described as bit commitment, maybe even more cleanly. Yes, a question?
So concealing is the same as what people call binding?
Oh, concealing?
Yeah.
Is it the same thing as binding?
Hiding.
Hiding, yes, thank you. Yes, some people, yes. Interchangeably, we can call this hiding. Concealing, yeah. The oblivious transfer, I'm not going to describe it. It's maybe even more simple to describe as bit commitment. It's a simple building block, and it's known to be, if you have the oblivious transfer, then you can build much more complicated things such as two-party and multi-party computation. So if we can only show that we can do a quantum bit commitment, if we could do bit commitment using quantum information, then we can do oblivious transfer, and then we can have all of multi-party computation. I should mention that classically, it's not possible to build oblivious transfer unconditionally, so we need computational assumptions. So then that means that we can't get this full multi-party computation using classical resources. So historically, because I want to give you like a history of what's been going on in quantum crypto, there was this excitement. Very exciting that, there was Wiesner quantum money way up the scale over here. In 1984, quantum key distribution. Super exciting that we can do this unconditionally secure a key agreement, which is something that you cannot do classically. 1992, super dense coding. I don't think we actually covered this. It's a cute little protocol. It has nothing to do with crypto, nothing obvious to do with crypto, but was one of these pioneering works. And then, this quantum key distribution made people think, well, maybe we can do, and the fact that we could have OT from commitments quantumly, maybe we could do quantum bit commitment. And wouldn't that be great? Because that would give us unconditional multi-party computation, which is something that you cannot do classically. And there was a claim in 1993, provably unbreakable bit commitment. Oh, there's no quantum in that title? That's surprising. Anyways, this was using quantum. Oh, by the way, quantum is a very overloaded term when it comes to cryptography. Maybe this hasn't been explained yet sufficiently. Wow, people are reacting to that. If you put quantum, it could mean many different things, right? Quantum multi-party computation could mean classical multi-party computation using quantum resources. Or it could mean computing quantum circuits in a multi-party way, probably using quantum resources also. So you have to really kind of think critically when you hear it to think, okay, what context are they actually meaning here? When I say quantum bit commitment here, I mean doing a classical bit commitment using quantum means. Quantum key distribution is similar, right? Using quantum means, quantum communication lets distribute a classical key. Okay, so where was I? 1993, provably unbreakable bit commitment. I would have said maybe quantum bit commitment, but maybe that's confusing. Anyways, so that was the claim. 1995, quantum teleportation, also a very exciting thing that you heard about briefly yesterday. And then, a big disappointment. Actually, quantum bit commitment is impossible. So these two results are contradictory. This was actually showing that the original one had a flaw. What happened is, okay, this is this proposal. Oh yeah, it was called quantum bit commitment, was provably unbreakable by both parties. And they made a subtle assumption in the definition itself, maybe an assumption that you would make if you were coming from classical or conventional cryptography. So the mistake is to assume that if Alice can cheat the binding property, then she knows how to open both a commitment to 0 and a commitment to 1. Knowing is stronger than being able to. So the impossibility proof shows that she's actually able to open a commitment to 0 or a 1. That's in a nutshell kind of what happened. I wanted to show you a sketch of the proof for the impossibility of bit commitment because it's useful to have this type of attack in mind if you're trying to come up with your own scheme and trying to see if it might be secure or not. Okay, so these were the two papers simultaneously published on the impossibility of quantum bit commitment. We'll do this version of the proof. We'll do the perfect version, so no trace distance required. There is an approximate version that also works. And we'll use the tools that Fang introduced yesterday, the Schmidt decomposition. Cool thing about the Schmidt decomposition, right, is that if we didn't know about this theorem, in general, you could write any state as a tensor product of two different bases. Then you'd have like n squared possible terms, but here it's like the actual same index of the bases. And also these coefficients are non-negative and real. Anyways, I just wanted to point that out. We did have a proof yesterday of the Schmidt decomposition, if I'm not mistaken. And we also had this result that follows from the Schmidt decomposition, which is the version that we want to use right now. So suppose you have two quantum systems on A tensor B. And suppose that if you trace out the B system, then the two states are actually the same. Okay, so that is saying that actually on Alice's side, if Alice has the A system, suppose that there's no difference whether she was sharing the psi or phi. This is another way of interpreting what this is saying, that she has exactly the same state. Her reduced density is exactly the same, whether they start with psi or phi. Then there exists a unitary U acting on the B system only that maps the psi to the phi. You can kind of see how this would be very, very useful for this impossibility proof of bit commitment. Okay, there's no perfectly concealing and perfectly binding quantum bit commitment protocol, so those are the two properties that we can work with. We'll assume that we have a protocol that's perfectly concealing, and then we'll break the binding. Actually, we'll completely break the binding. We're doing the perfect case, as I mentioned. Okay, binding means that she cannot modify the B, And hiding or concealing means that Bob cannot learn anything about B during the commit phase. Okay, so suppose that we have such a scheme. Suppose, without loss of generality, that all the operations are unitary. We can do that via the purification that we talked about yesterday. And consider the joint state after the commit phase. So suppose that Alice was committing to bit b equals 0, then we'll call this state psi 0. And if Alice was committing to bit b equals 1, we'll call this state psi 1. By the hiding property, Bob has the exact same system whether she sent psi 0 or psi 1. And by the way, this includes any interaction. So there was like debate, like, oh my goodness, this proof, maybe it's only applicable to like single message protocols because look, it's a single message. But actually the psi 0 is the result obtained even via an interactive process that we purify. Like that's the state just before the reveal phase. Okay, so we're saying by the concealing, Bob can't tell at all between psi 0 and psi 1. Oh, but that's exactly this condition about the trace, right? If we trace out Alice's system on psi 0, that should be exactly the same as tracing out Alice's system on psi 1, because this represents the density matrix that Bob has on his side in the two different scenarios. Okay, then by the corollary that we had of the Schmidt decomposition, there exists a unitary on Alice's side only. Okay, we're using it in the other way. The unitary was on the B system in the lemma, but here we're using it in the other way. So there's a unitary on the A system that maps psi 0 to psi 1. Okay, so it means that because Bob can't tell what she's committing to, she can change her mind. She can completely change her mind at will by applying the unitary U. So her most basic attack would be to fake the commitment to a bit 0, and later on, when she decides what she wants to say, what she wants to open, she'll apply the unitary U if she wants to open the bit 1. If she wants to open to the bit 0, well, it's already 0. So like commitment, you can kind of see it as kind of like, oh, I'm betting somebody that I can predict an outcome, you know. I'm betting I can tell the weather, tomorrow's weather or something. And like you put the bet in a safe, you send it over, and later on when the event actually happens, we verify if my bet was correct. So this is saying I can change my mind. It's not at all binding. Yeah. So therefore, like, there's no hope of getting the quantum bit commitment. And the take-home is this purification is an attack. It's an attack that an adversary can do, trying to come up with a protocol. You better double-check what happens if you purify it, and does that enable any cool things on, well, cool things. Does that enable types of attacks that you haven't maybe considered yet in your proof?
If she can apply transformation, doesn't that seem to imply that she hasn't handed over the thing yet?
Oh, thank you. So the question is, if she's applied a transformation, does that imply that she hasn't handed it over yet? When we wrote the psi 0, it's a joint system on A and B. The B part is what she's handed over. We don't know, we haven't really written what she's handed over. All we know is it's the B part of psi 0. And similarly for psi 1. So it does mean because she has this unitary, she can change her mind into what was the bit that she had actually committed to. Yeah. Purification is a way sometimes to delay operations. It's really, yeah, because she's kind of, by purifying, she can delay what her choice is and decide later. Yeah.
So it seems to use the assumption that A and B are finite the workspaces, and the available operation you can do is all the bounded unitary operators. But if you consider some extended system where only local, there's some notion of like limitation on what kind of unitary A can apply to the system. It could be that it's impossible. For example, if the unitary is like flip all spin, if there are infinitely many of them, or effectively infinite of them, then flipping all of them would not be an option. I think flip everything on A side. Something about it is using the fact that for finite dimensional system, like operators are very powerful, but for infinite dimensional system.
Okay, thanks for that comment question. For those who were behind and couldn't hear, the comment is that maybe for this analysis is assuming finite dimensional systems, and that's true. We're kind of, I guess since the beginning of the lectures, we've been in these finite dimensional systems, and the question is, well, maybe if they're infinite dimensional, there are operations that are forbidden, like spin flips. Okay.
Yeah, so for example, if the infinite dimensional come from the fact that your system is a large number of things, and you can only do geometrically local things on it.
Okay. Yeah, it's possible. I mean, I don't know how to fully answer that question. If we add extra, or if we have access to extra limitations on the adversary, it's possible that this proof would not be applicable. And actually, we have a couple cases in the finite dimensional case that I'll quickly mention coming up.
Wouldn't it be a form of a computational assumption?
Sure, but it's like
So as the comment was, maybe that's a form of a computational assumption. It's an assumption, so I don't know if it's like a physical, hardware, or computational or something, and then maybe this is not applicable. So it's good to it's good to double check what are the parameters of this impossibility. And actually, I even tell my students, like, don't believe impossibility proofs. Like, there's always like, what's the exact scenario that they're proving impossible? And like, maybe that's not what you're thinking. Maybe you should double check that, what's the applicability of that impossibility. So, good point.
So another comment is that if the way that quantum memory is built is actually by topological methods that Microsoft is pursuing, then this computational limitation will be built in some sense.
Yeah, it's a good question of how these translate to the actual systems that we have right now. Okay, and as I mentioned, we also have the approximate case that holds of trace distances and all that stuff. It also works. Possibilities for bit commitment. So a nice comment that started this discussion. Well, if we're willing to make extra assumptions, then bit commitment becomes possible, namely computational assumptions. Like this is well known for classical bit commitment. Never mind, there's no quantum in this. So usually we can get one or the other. We can get statistical binding, computational hiding, or computational binding, statistical hiding. Using physical assumptions, we can also get information-theoretic quantum bit commitment. So that means using quantum resources. So there's been some really nice work on bounded quantum storage. So let's limit the storage of the adversary. And then the idea is that we can get a bit commitment. Similarly, noisy quantum storage. So let's assume that perfect storage doesn't happen, so there's always some sort of noise after a certain time, and then take advantage of that for cryptography. Yeah?
For the bounded quantum storage model, is it like a polynomial bound or
yeah, the bounded quantum storage is, first of all, the honest parties need no storage, and the cheating party, it's the recipient, and I think it's polynomial. So we're saying that an adversary would need more than polynomial. I think it's more concrete than that. I don't know if anybody knows here. There's like a concrete bound that if the adversary would need so many qubits, and it's not that big to break it. So it's not exponential or something like that. I don't know, I'm not sure. Dominic?
I think it was linear. So if you have the communication is bigger than what the adversary stores by maybe some constant factor or something, then you're safe. While I think in the classical case you also get bounded storage stuff, but there you have a quadratic. You need quadratically more communication than the
Okay, yeah, thanks. So you're saying classically there's also bounded storage, but they require quadratic, and then quantumly, what was that? I just can't hear it.
Linear.
Linear. Even linear. Thanks.
I mean, I'm not fully swearing on it because I also just off the top of my head.
Yeah.
I've done
Yeah.
it years, and I think it was-
Yeah, that sounds right. And then also isolated qubits, so assuming that there's no multi-qubit interactions within the systems. And all of these they're motivated by limitations of current quantum technology. So these are all reasonable, it's all reasonable to think that an adversary would have such physical limitations. I think that's all I had for bit commitment. Are there any further questions? Yeah.
Yeah, is there a useful notion of qubit commitment?
Oh, okay, yeah. So like this quantum and bit commitment. So would there be like a qubit commitment type of thing? We want to commit to a qubit. I've used things like that where you do like a hybrid. Well, if you have a quantum state that you want to put it in a box, like a safe kind of thing, let's like encrypt it with a classical key and then commit the classical. We haven't talked about this yet, but there is a way to encrypt a quantum state with a classical key. Commit to the classical key using a commitment scheme for classical data, and then it's kind of like the quantum state is also committed. I don't know if anybody's really formally defined all of that though. Yeah, that's what I had for commitment. Okay, the next topic I want to tell you about is delegating private quantum computations. This is more along the lines of computations and like a type of cryptography within computations and quantum computations. So that's a different type of computation, right? So we use a quantum circuit, we operate on qubits. Okay, so here's the general picture. You have a client, computationally weak, you have a cloud or server, and we want to upload some data, maybe just for storage or maybe for like computations. We want to compute on that data. But you can easily come up with situations where you would want some privacy, like your online income tax software. You wouldn't want the cloud to have access to that actual data. So private computations would want to upload the encrypted version of your data and then still be able to get something useful out of it, like the function of the data. So this type of situation is referred to as homomorphic encryption, and some very early work in 1978 alluded to the idea that maybe we could have encryption schemes that would allow operations. It's very counterintuitive. Like you're uploading stuff that should be garbled, like random, it should look random, and yet you still want to be able to, the server should still be able to compute something on it such that when you get it back, then you could decrypt it. So, these authors were saying, well, complicated operations seem to require that the data be decrypted before operating on. But the same paper points out that actually plain RSA is multiplicatively homomorphic. You can do multiplications on ciphertexts, and that implies multiplications on the plain texts themselves. So these are the ciphertexts, and then you can simply multiply them. And that is the same thing as the underlying multiplication of the plain texts. So maybe there could be a hope of achieving homomorphic encryption. And for a long time, that was a question, and like the big surprise was in 2009 when Craig Gentry showed that there was a way to do fully homomorphic encryption actually using lattices. We want to talk about quantum computations. For instance, maybe you want to delegate a Shor's algorithm. You want to use a quantum server to run Shor's algorithm. You don't want to tell the quantum server what is the key or what's the RSA public key that you're trying to break. So you want to hide the input maybe you want to process quantum data in a private way, like processing quantum money or quantum coins. And of course, these slides are from a while ago. It's even more relevant that we actually have quantum clouds now. A while ago, we didn't have quantum clouds, so it's very relevant looking at what the architecture is probably going to be when we have access to quantum computers. For now, we're going to limit ourselves, I don't know if it's a limitation, but we're going to look for information-theoretic security. We're going to be okay with interaction. And the client, ideally, the client would be fully classical, so I could do this on my laptop and accessing a quantum computer in the cloud. The thing we're going to do now, the client has a little bit of quantum power, and I'll tell you what it is shortly. The way I'm presenting it today, it's from this paper of mine, and there was actually also an experimental demonstration. The concept is actually called blind quantum computing, and the blind quantum computing was originally proposed in the measurement-based model for quantum computation, which is an alternative to the circuit-based model. But since we haven't done measurement-based computation, let's stick to the circuit-based implementation, and that's better described in this paper here. Okay, so the client is actually going to have to send random qubits. These are the exact same random qubits that we had in the QKD. So ket 0, ket 1, ket plus, ket minus. These are completely independent of the actual circuit and whatnot you're trying to do. It's kind of like an aid in the delegated computation so that you can keep retain privacy. So the idea is that the input is a quantum circuit. For now, think about the quantum circuit as being public, and what we want to do is hide the input. Did we talk about universality of quantum computations? Yes, okay, so there's, classically, it's very simple universality. You need the NAND gate, and then you can do any classical computation quantumly. It's much more subtle. Without going into the details, we'll use the following universal set of quantum gates. It's actually slightly redundant, but it's kind of useful to think about it this way. We have the X, Z, P, Hadamard, and control not. These are called the Clifford group gates. And the group generated by all of these is called the Clifford group. They have some nice properties. For universality, and these ones are called the Pauli gates, X and Z. For universality, we need to add an extra non-Clifford operation, and we'll choose this one. In this slide, it's called R. As I was mentioning, I made these slides a long time ago, and at that time, the jury was still out whether we'd call this R or T. Okay, go figure. T has 1. Okay, so now this is called the T gate. It's also called the pyrite gate. Because of course there's there's no pyrite, but there could be a pyrite if we want to scale this by something. Anyways, strange terminology. It's the square root of P is the important part. Okay, and for universality, we also need single qubit preparation and single qubit measurements, and then you can do any quantum computation. So let's try to hide the circuit that we're doing. No, it's hide the input that we're doing, and yet still be able to do these quantum gates. And that way you could get any quantum circuit. In order to hide the input, we'll use the one-time pad. We've talked about the classical one-time pad. The quantum one-time pad is a quantum version of the classical one-time pad. We want to take a qubit and encrypt it. And it turns out that even if it's a quantum state with infinite information or something, like infinite degrees of freedom within a single qubit, you only need 2 classical bits to encrypt it. Namely, we'll choose A and B uniformly at random, and if we apply these 2 polys, so this means if A and B are both 0, then you do the identity. If B is 1, A is 0, you just do the X. If they're both 1, you do X and Z. If A is 1 and B is 0, you just do the Z. So there's 4 possibilities of unitaries that you would apply. And if you choose one of those unitaries randomly, then you will actually be fully encrypting the quantum state. And we can show that because without knowledge of the key, the ciphertext is always in the maximally mixed state. Okay, so yes?
Why is the Z necessary? Why can't you just use X?
Okay, great. So in this quantum encryption, why is the Z gate necessary? Why could you not just do X? Okay. Because of these states. Okay, if you do an X on a plus, it's actually unchanged. And if you do an X on a minus, it's also unchanged. So then the adversary would be able to distinguish whether you had encrypted a plus or a minus. So then the Z acts as an X in the Hadamard basis. So that's, did I say Z? Yeah, Z equals HXH. So that should at least take care of my counterexample that if you also do a random Z, you'll also encrypt these ones, and it turns out that that's sufficient. So let's encrypt the input using the quantum one-time pad. The red, okay, they're red on my screen. You probably can't tell the difference. These superscripts are the keys. So the wires are the inputs, the quantum input state coming in. The client will encrypt the input and then send it to the server, starting here. And then the server will be doing the gates. This is the target circuit in our toy example. The data is encrypted with these one-time pad keys. So we have to find a way to play around with the one-time pad keys so that the client, from her point of view, can update the keys and understand what's going on, while the server can still do something meaningful without actually needing to decrypt the message. So these two contradictory things come together, and we nevertheless manage to do this. At a high level, we have these keys on the wires, and we'll go into different gadgets. So based on the underlying circuit element that we want to do, they'll go into this sub-protocol. And so say they do a sub-protocol for the R gate, then then there's a possible key update rule that the client on her side can compute, knowing that we've just gotten into that sub-protocol. Similarly, for all of these, we still have the 2-qubit C0 gate where the wires will be updated, both of the wires will be updated, et cetera. Okay, so et cetera. And the point is that at the end, the client has computed the keys to be able to decrypt. And when she decrypts, she'll get the output of the actual computation. Are there any comments and questions about this kind of setup? Yep.
So does that mean that the client needs to know exactly what the computation, how the computation is implemented?
Does that know that the client or server, what did you say?
Client, does it need to know the exact implementation, or in other words, does it depend on what the circuit computes, or does it depend on the circuit?
Okay, so does the client know the actual computation?
Well, I mean, the client obviously wants a certain computation done, but the computation will be implemented by different circuits.
Oh, okay.
So is it automatic that the adjustment of keys is independent on the circuit and only on the computation that has to be done?
Oh, okay. So I think the question is for a fixed computation, there could be many circuit implementations of that computation. And how does this technique deal with that? We're going to fix the circuit implementation, and the protocol is going to take that as the input parameter type of thing. So, yeah. So there's no, if you had a different circuit implementation, you'd run a different protocol.
I think I'm confused by what you're writing here, but is the client doing as much work as the server?
Oh, not at all. So the client is doing the encryption, which are single qubit random polys, and the server is doing all of this.
Okay, so then these A's and B's are just like implicit. I mean, the server doesn't know them clearly.
The server does not know the A's and B's
Okay,
clearly.
and then at the end, when the output is sent to the client,
Yeah.
what does the client do with
The
it?
client is going to do the polys, the X conditional polys based on these new updated keys.
But how does it know those updated keys?
Oh, because each gadget, which I'll tell you, will tell you how to update the key from the client's point of view.
But the client is not computing those? I mean, is the client tracing through one by one and computing all these intermediate values?
Yes, all the intermediate values are the keys. This is all classical computation.
Right, so instead of, quantum gates, it's doing K classical gates.
Yes,
Okay.
yes. There's obviously, yes, it's a good point. There's obviously a cost to doing this. The difference is that,
Yeah,
it's not quantum,
Yeah.
so like that's the huge gap, right?
Yeah.
Try to do a T gate, like R gate. You can't do it. Yeah.
How are these homomorphic though? I mean, they're right. So when you do homomorphic
Yeah.
addition, that's you can't just pick random numbers. Addition to that.
Right, so it doesn't map exactly to the homomorphic case because it's interactive and there's like these key updates. So it's more like an interactive delegation. But it has the spirit of homomorphic because you can do computations on the encrypted messages. Okay, so the simple protocols are like if Alice wants to prepare a qubit in ket 0, everybody knows that it's a qubit in ket 0, so she sets the key to 0 as 0, 0, and creates this auxiliary qubit. For a measurement, Bob is going to be doing the measurement. Say the qubit is coming in, it's encrypted with A, B, so that's x to the A, z to the B. The measurement, it's going to be only on the computational basis, will be flipped if and only if A is equal to 1. Okay, the B does not make, it's a Z, it's on the Z, poly Z, it doesn't change the outcome of the measurement because we're measuring the computational basis what's more. So if the server returns a classical bit string, Alice flips it with x to the A, and that's it. So the Clifford group gates have this nice property that they are the set of operators that conjugate polys into polys, meaning that if you have a poly key and then you do a Clifford operation, by definition, you know that there's a poly update key. And they're pretty simple for the X and Z gates. Actually, the server can simply do the X and the key stays the same thing for Z. Hadamard is slightly more complicated. It flips it inverts the role of A and B. P does something also slightly more complicated. You need to do this XOR, and the control NOT, you can double check that it has this property that you need to. This would be the key update after the XOR, these two wires. Control NOT, sorry. That would be the key update after the control NOT. The tricky gate, yeah.
I mean, just take a simple case where I encode a single qubit and B, and then the server applies a Z gate and then sends me the result back. I mean, doesn't the B flip after applying a Z gate? I mean, it's like Z times x to the A Z to the B.
Yeah. No, it doesn't. So you would have x to the A, z to the B, and then you do a z.
Yeah. So let's take A0, for example. It doesn't really matter what that's saying.
Yeah. So that's equal to z to the B, z. Okay, and then the point is that you have your cipher, your plain text is here. That's the plain text, that's the encryption. That's the encryption. Okay, and then if you do a z gate on it, well, it's the same thing as doing the z on the plain text up to this encryption key. So the polys have this, like the commute. Yeah, they just commute. Basically, they just commute. And then these other things, like the Cliffords, they almost commute with the polys. You just need to kind of change it. So this one with the Hadamard, it's saying that H, x to the A, z to the B equals z to the A, x to the B, H.
So it's a commutation relation.
Yeah. For universality, we need the extra R gate, and that's the tricky one. By definition, it's not going to have this nice key update. Namely, if you tried to apply the R gate on something that's encrypted with x to the A, z to the B, you would get this. This would be your update, and notice that it has this non-poly. It's a P to the A. It's still a Clifford, but it's a non-poly. And you could try to carry that P to the A all through your computation, but then it blows up because it doesn't work with the other gadgets, etc. So we're going to overcome this difficulty via some interaction and an auxiliary qubit. Okay, so the main idea is the client is going to make the server correct this P error. So notice that the P is conditional on A. A is the key. We can't tell, we can't give A in the clear. That would be the key. So the server is going to correct this P error by making him apply a hidden P correction. Right, okay, so this is the gadget, and it gets more complicated. We have the client that's preparing some auxiliary stuff and sending it. That's what it means when there's a wire going up here. The server is at the top. It has the wire and the circuit that they're actually computing. Initially, the encryption is A, comma B, as usual. The server goes ahead and applies R on that encrypted message. That's going to apply the R up to this correction. Then we go into this slightly more complicated thing to do the P correction without the server knowing that they're doing the P correction, as I mentioned. Okay, so at this point, this is the update, or the poly, it's not a poly key, or this would be the correction, let's say. So the client is going to send a random auxiliary state containing a hidden P gate. So in a way, Y and D are both random. So this is like hiding whether or not your auxiliary state has a P encoded into it. Because you're in this plane, the plus, you only need one bit of key, so just a Z to encrypt that. You send that over to the server, and the server kind of does this control not. Okay, these are the 4 possibilities. So I slightly lied to you that this is plus, minus, and I call this one ket plus and ket minus. They're the eigenstates of the Y poly. If you know about those, it's still 4 states that are unitarily equivalent to the BBD, conjugate coding states. Okay, so then what's going to happen is that the server is kind of going to teleport through this auxiliary state so that this operation, this hidden P, is applied, but he doesn't know. So we do this with a control not. It's an entangling operation. The client sends a classical bit, which is A XOR Y. Note that this A is the same as A is here, so we want to absolutely hide that. This Y is the same Y as here. This is hidden by this D. I mean, at least intuitively. That's a classical message, and then the server does a conditional P based on this value X. And the net effect is that we have this P correction, so they kind of cancel out. If A is 0 and if A is 1, then the P is actually applied. And then we have these 2 quantum registers. We only want actually 1 because we want this output wire, and this measurement is going to kind of teleport that outcome into the output, into this wire which will become the new kind of wire in the computation. There is a measurement outcome that is sent to the client, and the client knows how to use this C in order to update the encryption key. And this is actually the key update. So this is the new X part component, and the Z component has a multiplication notice. So this is the only gate that has multiplications in the key updates. Okay, so that's a bit of a mouthful. But when you look at it piece by piece, it kind of makes sense that they'll be able to correct this via the interaction. Are there any questions? Okay, so why does this work? Well, we use some circuit derivation techniques, it's kind of fun to work with different circuits and see what they do, and then add different components to kind of modify them into larger circuits and eventually get to the goal that we want to do here for this R-gate protocol. And I think some of these basic ones were also in your exercises. So there's something called the X teleportation. We've talked about full teleportation yesterday. The full teleportation has a full poly correction, X to the A, Z to the B. And this one is kind of like a partial teleportation. If you have a state psi, and you have an auxiliary plus, and you do this control not and a measurement, you've actually, on this bottom wire, you've managed to teleport the input up to some X correction. It's not as useful for like an Alice and Bob teleportation. It's kind of useful as a circuit gadget. In order to get to where we want to prove that the correctness of that scheme or that circuit that we had in the previous slide, let's modify some things. For instance, if we change the input, add a poly encryption to the state, and then also do an OR gate on that encrypted thing, well, we just change the psi becomes this new psi, which is R applied to the encrypted input, and then we know by the previous calculation that I didn't show you, but I claimed that this would be the final outcome. Remember, it has this P to the A correction. We can add rotations to the bottom wire. These are Z rotations, and they're all kind of like the same family in the same plane, P to the Y, Z to the D, and then P to the A XOR Y. And they all commute with this control. And so we can plug away at simplifying the output. So they're all kind of, they commute with control. We can see them as all being applied at the very end of this calculation. So then we have what we had originally, and then a bunch of P, Y, Z, D, P, A, XOR Y. Then we can use a bunch of identities that how we can commute or almost commute these unitaries. I'll let you work that out if you'd like to, that this is the final simplified form. What this was so the point is that we just have an X and a Z, and this is the update key for the X component and for the Z component. So that is for correctness of this gadget. And now we have all the elements of the actual protocol, right? Because we know how to do each of the elements that form a universal family. What about security? And honestly, like sometimes getting the security definition is, well, I know probably a lot of you know about this, like that's the very tricky part. And I think this was the first time in this paper that we had the full security definition also in terms of side information. So like what if there's an input, but the adversary has access to the side information on that input. And nevertheless, we can still show security. So how do we formalize that the server learns nothing from its interaction with the client? And we can get some inspiration from conventional cryptography where we have the simulation paradigm. So simulators are things that help us formalize what it means to learn nothing. Namely, if we can emulate the channel, let me show you the picture. I think it's helpful. Okay. This is an actual protocol. We have the client, the server. We have an input. The input comes from elsewhere, sometimes called the environment. And part of the input will be sent to the client, and part of the input could be kept by the server. Yeah, part of the input could go to the server. So we want to formalize that the server does not learn any further information via the interaction with the client that they cannot get from this S part of the input already. So this forms a channel. There's an input, there's some communication going on here. Let's put a box all around that, and then the server outputs something. And that's a quantum channel. And on top of that, we'll say S prime is a deviating server. So the server doesn't have to do what they're told to do. They could try to do anything else to try to gain information from this protocol. A simulator, S sub S prime for S prime, is a general quantum circuit that agrees with S prime on the input and output dimensions. Okay, so this is a simulator. It has access only to the S system. The other system goes in the garbage, and it outputs something. Okay, so we're saying that these input and output dimensions agree. And we'll say that the protocol for delegated quantum computation is secure if for every S prime, there exists a simulator S sub S prime such that these channels are indistinguishable. Note that the simulator has no access to the C system at all. Okay, so if we're able to show that these channels are indistinguishable, this is also called ideal, the ideal case. it means that the real case is close to the ideal case. Since the ideal case is secure by definition, it means that the real case is also secure. So it's a very important paradigm to have in mind when you're trying to come up with your definition, and it also gives you a hint of how you should build your proof. In order to prove security, we would have to build a simulator for every S prime and show that these channels are indistinguishable. Oh, I talked about channels being indistinguishable. We actually don't have a formal definition of what that is. It happens to be what's called the diamond norm in quantum information. It has same thing as before. It has a mathematical definition. What's more important is the operational definition. It is, suppose that two channels agree, phi and psi agree on their input and output spaces. And given that one of the two is applied with equal probability, the optimal procedure to determine the identity of the channel with only one use succeeds with probability 1/2 plus the diamond norm of these channels divided by 4. So we'll use diamond norm as the proxy of indistinguishability of quantum channels. That's sufficient for our purposes. Oh, in this definition, the max is what? Oh, okay. Thanks. The max is also on W. I don't even know. Is it bound on W?
Yeah, and without loss of energy, it would be square.
Oh, yeah, by like side spring dilation, it can be most dimension. Okay, yeah. So the proof says, that definition tells us that we'll need to build a simulator. And once more, purification will come to the rescue. We kind of look at the protocol and purify it, and maybe then you'll notice that actually that gives you an idea of how to build the simulator. So the main idea is that we're going to change the client's protocol on the client side such that the server can't notice that it's changed, and the protocol is easy to be proven secure. Once more, we'll transform the protocol into something that's more difficult to do technologically, namely shear entanglement, however easier to prove secure. So instead of sending encrypted qubits, the client is going to send half EPR pairs. This is a really interesting link between teleportation and the quantum one-time pad. Notice that in teleportation, there's a poly correction, x to the a, z to the b, and those are uniformly random. But that's also exactly the operation to do a quantum encryption of the quantum one-time pad. So in a way, half of an EPR pair is an encrypted quantum bit. And which bit it is, which quantum state it is, well, you can decide later by teleporting in your quantum state. I'll just let that sink in. Okay, so a half EPR pair is like an encrypted quantum state. And you can decide later what you want to encrypt by teleporting in. Super useful. Okay, that's step one. Same thing for the auxiliary qubits. They're also generated somewhat in this random process, and you could see them as being sending half EPR pairs and deciding later what you're actually going to teleport in for the auxiliary qubit. And then, by this idea that you can change the order of the operations and decide later what your input is, the client delays inserting her actual input until after they're done all the interaction and all the computation. So it's like, okay, Bob, I'd like you to do this computation for me. Here's my encrypted input, but she doesn't tell him that it's actually a half EPR pair. Bob does all the computation on the half EPR pairs, finishes the thing, sends her everything, and she says, thanks a lot, and then she decides to teleport in, blah, 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 do her calculation. I'm not suggesting you actually do this for delegation, because that is very costly on Alice's side, the client side. I'm suggesting you do this for the proof. Okay, and then the protocol is trivially secure. You actually do not need access to the input at all, and you've already emulated this entire channel on this side with your simulator. And okay, well, I don't know if this is giving too much credit to Shor-Preskel, but it's this idea of purification. Okay, very useful. Okay, so as I was saying, instead of sending an encrypted qubit, the client will send a half EPR pair. This is an EPR pair. And she sends this for encryption. And as I was saying, it's kind of like delaying her input, and it's an encrypted state on the server side. And later on, she can do this Bell basis measurement to teleport in her input. So we'll do this for all the inputs, and the server's view is the same. For the Clifford gates, there's nothing else to do. It's exactly the same thing. This R-gate subprotocol is slightly more complicated. So we can see that instead of sending auxiliary qubits, the client can send half EPR pairs and then kind of delay her measurement until later. And similarly, this bit, which was originally A XOR C, can now be chosen uniformly at random. So that's useful because it's uniform random information that can be simulated. This hidden P gate is now chosen as a function of A and X. This is this P to the Y, A XOR X, but notice that Alice does this now, the client. And the value of D is now determined by a measurement. So that was the D previously, which was Z to the D on the auxiliary qubit. And we can do this for each R-gate protocol. And the point is that the server's view and the effect of the protocol is completely unchanged. And of course, we've managed here to delay actually having to teleport in the input until the very end. We do this for each subprotocol, all these delays for the input and each of the T gates, R gates, and that's how we get our simulator. So the simulator is the same no matter what the input, and it does these delay operations. So we generate the simulator that generates the transmissions that the client would send in the protocol, and feeds them to the S prime, which it internally simulates, but that never performs any measurements. So it doesn't do these final measurements because they're not required, because by that time the server has given their output. Access to the actual input is not required, and therefore the view of S prime is unchanged, and that means that these two channels are actually identical. Which we can rephrase in terms of the diamond norm. So that is the protocol and the proof. So we have this method to compute on encrypted quantum data, and it's rather technologically easy from the client side, but it's not fully classical. I'd like to tell you, I guess, just briefly, what are the kind of related concepts, and there's lots of, this is an ongoing topic of current research in terms of, Okay, so as I mentioned, there's this universal blind quantum computation, which was the original one, and like interestingly enough, it came out the same year as fully homomorphic classical encryption. So it was kind of like going on at the same time of like, oh, okay, we know how to do classical FHE. Actually, I didn't even know about FHE when I did this. I was like, oh, okay, look at the link. And then, but we did this in a different model for quantum computation. So it's slightly more complicated to explain to this audience. There's a related, really interesting question, which is of verification. Okay, so we're saying that we're going to use a quantum computer, delegated computation. We're saying we're going to delegate a quantum computation. The expectation is that these are things that are difficult for conventional computers. So how do we know that the output is correct? We can't compute it on our side, which is why we're delegating it. It seems to be like an impossible situation, right? How are you going to check something that you can't verify yourself? You could do maybe verify small systems and then gain confidence that the larger systems are behaving correctly. But actually, like in complexity theory, we have ways to deal with this, right? They're called interactive proofs, and we know that the power of interaction is very large. IP equals P space. You can verify a lot of things via interaction, even with a polynomial bounded classical computer. So let's use that idea of interaction also in the context of quantum computations, of delegated quantum computations. And there are methods to deal with this. So consider factoring. Okay, this is not the most general case, we can efficiently verify a solution if a quantum computer gives us a claimed solution. But these are the problems that are in, what am I looking for? They're in BQP, but not BQP complete necessarily. How can you become convinced, blah, blah, blah. So we know of bootstrapping methods. So if experimentalist is convinced that she can characterize and control a small quantum system, then we can expand this to an entire quantum system. And that was actually done for blind quantum computing in this work that kind of has these trapped qubits. And the idea is that those qubits, we kind of intentionally put them there, and we expect a certain measurement outcome. If we don't get that, then we know that there's been a deviation. That idea can be broadened to also the protocol that I just showed you about delegating quantum computations in the circuit model. We can kind of randomly choose whether we're going to do a test run or a computation run. And the test run is going to be doing a known quantum computation, namely the identity on 0. Okay, we know the output of the identity on 0. The output should be 0. And then the actual computation runs will be the runs that are meaningful. And the idea is that we'll use the cryptography, namely indistinguishability from the point of view of the prover, of the server. The prover won't know if they're being tested or if they're doing the computation. And the point is that any type of deviation will be caught in a test run or will have a negligible influence on the output of the computation. Yeah, okay, that's just a summary. Either the prover is benign and the output is rather correct, or the prover is not benign, it's doing something really kind of deviating and changing the output, and that's detected in a test run. Yeah?
So in this case, is there any more resources shared?
Yeah, the resources here are exactly the same as in the non-verifiable protocol that we had previously. Also, interaction for the T-gate. Okay, coming up. Yeah, so classical verifier, right? So the question is, are there any results where the verifier is completely classical? So that would be really desirable that you have just on your laptop and you can interact. Well, the first type of results in that area came out with 2 isolated provers. So these are quantum computers. They're quantum polynomial time, so they're still reasonable quantum computers. And they're separated, they're isolated, they interact with a classical client. And the idea is that the client is able to take advantage of the fact that they're separated to kind of cross-interrogate in a quantum way and become convinced that a certain computation is being performed. So they're kind of going to intertwine a cross-interrogation with the actual computation. And that's going to be able to delegate a quantum computation in a verifiable way. The next steps would be to make that a single server, and we know how to do that using computational assumptions. So fully classical client, computational assumptions, quantum server, and you can delegate a computation verifiably. Yeah. In this one, the servers, for completeness, they'll need lots of entanglement. Yeah. Yeah. This is the realm of what's known now as self-testing. The 2 servers, the 2 provers, or the 2 servers, they need to share lots of entanglement in order to convince the verifier.
And the last one?
The last one has no entanglement.
But still 2?
No, single, yeah. I kind of got lazy with the pictures. The last one, using computational assumptions, a single classical client and a single quantum server.
And no shared entanglement?
No quantum communication whatsoever, no pre-shared entanglement. Yeah, so they're going to use computational assumptions to kind of emulate the idea that there's some unknown quantum states that the server has.
Like decision problems,
Like what type of problems they're doing?
computations in general.
Yeah, like a BQP computation. So you have like a quantum polynomial time server, and they could do the computation in a verifiable way for the prover, for the client. Yep.
Like computation and one is interactive. Is that the only difference?
Yeah, the question is like, what's the link between homomorphic encryption and blind quantum computing? Yeah, the blind quantum computing is interactive. Plus the client chooses the circuit. Homomorphic encryption, it's non-interactive, and the server chooses what they want to apply. There is a quantum homomorphic encryption also, which is homomorphic computations on quantum ciphertext to do quantum circuits. That's also solved by the same author and maybe some other collaborators using computational assumptions. Okay. Do I have 20 minutes?
20 minutes, yeah.
Okay. Yeah, any further questions or comments from so far on any of the topics or techniques? I don't want to necessarily rush through if there's more discussions. Mm-hmm.
So on the delegation part, maybe you've already answered this. Is it known whether the client could be completely classical, share no entanglement of quantum resources, nevertheless delegate securely a quantum computation to a server with purely classical data, going and coming back?
Yep, that one is computationally, that's known how to do it with computational assumptions, LWE actually.
Learning the layers.
Yep.
And you showed this in your slides?
No, I only alluded to it in the last slide, like Mahadev, and it said like
That's fine.
classical client, one server, computational assumptions.
That was verification, this for delegation as well?
Okay, yeah, well, verification, I guess, is strictly more powerful than delegation. So it implies delegation.
Yeah, so secure, like blind.
Yeah.
So encrypting your computation, it's about homomorphic. So you should
Encrypting the data.
Yeah, encrypting the data, getting it back. You can do that within the algorithm framework.
Oh yeah, so actually, if there's no verification, it's called homomorphic encryption. If it's a non-interactive, and the server can choose the input, the circuit, and that we also have quantum fully homomorphic encryption. Yeah.
Really classical.
Purely classical client, classical communication, quantum server under computational assumptions.
Thanks.
Okay, so let me get into some more recent stuff. And this is an overview of certified deletion. It's another one of these things that you can do quantumly using quantum encodings that there's really no, it's really trivial to see that it's impossible to do certified deletion with classical communication. Here's the physical analogy to start the story. The thing starts with Alice inserting a message into a safe, closing it, and sending it to Bob. We've seen this before. Okay, what's going to happen? He gets the message. Now this is now different from commitment. So Bob can decide he has this safe. So he can decide to return the safe before the combination is revealed. He just takes it, sends it back to Alice. And for Alice, that's a proof that he didn't read the message. and he's never going to have access to the message. It was in the safe, he had it temporarily, he gave it back, and she knows that he's given it back. XOR, okay, he can do this or the other thing, but not both. He could keep the safe, and when the combination is revealed, he can open and read the contents. Why would the combination be revealed? Well, maybe that's by design. Maybe eventually Alice reveals the combination, or maybe it's a eventual leak of the key. Maybe it's we used RSA and somebody's managed to factor. For some reason, the key is now available, and then he could read the contents. Okay, and notice that because of the physical analogy, he can do, I repeat, one or the other, but not both. So we would like to be able to emulate this in a digital world. If we're using a classical encryption, say Alice were to encode a message with a key K and send that to Bob. Well, Bob can make a copy of the ciphertext. That makes him these 2 copies. And he used the first copy, so it's a proof by contradiction. He uses the first copy to convince Alice that he did not read the message. Like whatever the scheme says to do to convince her that he didn't read it, he does that with the first copy. He uses a second copy to wait until the combination is revealed, open, and read the content. So clearly, with classical information, we're not going to be able to get certified deletion. We're not going to be able to emulate this type of safe that can be returned, and that returning is really a proof that the data is not going to be read. So here's an application of certified deletion. If only we could do this. Say Alice has her last will and testament, and she sends that to her lawyer. And maybe she encodes that first with certified deletion. Then say she wants to update her will, then it's convenient if the lawyer would first prove that the initial will is deleted. Maybe this is like, she's changed her mind. She doesn't want anybody to ever know who was her original, who was originally going to get such and such property. So this would be very convenient. The lawyer could prove that the original will is deleted and update it with a new version. Of course, if we're talking about this right now, in this session about information-theoretic quantum cryptography, it's because with quantum encodings, we can get this certified deletion property. So we get, in a way, the best of the physical and digital worlds, and that's kind of been the underlying story here today, starting with the Apple, the safes, etc. We have these physical analogies that map much better to the quantum world, because it's probably not a coincidence. I mean, the quantum world is closer, maybe, to the actual physical description of reality. So we'll encode a classical message into a quantum state, and then Bob will be able to prove that he deleted the message by sending Alice a classical string. So it's not exactly like returning the safe, it's more like proving that the safe has been deleted. You've seen this before. We're going to use the idea of conjugate coding. And here is a toy example that gives you the concept. So here there's going to be 4 bits, 4 qubits in the encoding. We'll choose a random R, and a random theta and a random R. And we'll give the Wiesner or conjugate encoding. That's going to be the quantum encoding of the message. Where's the message actually? It's not there yet. R comp is going to be the substring of the R encoded in the computational basis, and R diag is a substring of R encoded in the diagonal basis. Okay, yes, where's the message? It's going to be one-time padded with R comp. So we'll send along with R theta, which is these 4 qubits, we'll send M XOR R comp, which is these 0, 1. So this is going to be for a 2-bit message. How do you think we're going to delete? How do you think Bob could kind of prove that he's deleted R comp or the message? Is there something that, if you knew that this was the kind of encoding that was prepared, is there something that would maybe convince you that the message is deleted. Yeah? Exactly. So if Bob measures in the opposite or complementary basis to our comp, right? Because our comp is in the computational basis. If you measure a qubit in the computational basis, if you measure it in the diagonal basis, it erases it, right? Because it kind of randomizes that bit. Notice that if you measure R theta, all the qubits in the diagonal basis, actually, some of those outputs are deterministic, namely the ones that were already encoded in the diagonal basis. So to delete the message, measure all the qubits in the diagonal basis. There's some wildcards here, the stars. Those are the ones that were originally in the computational basis. They will be uniform. And these ones are deterministic. One, you need to have a 1 here, and you need to have a 0 here. So we're kind of simultaneously using the property of the diagonal basis being deterministic when you measure in the diagonal basis, and these ones being made uniform when they're measured in the diagonal basis. So to verify the deletion, we'll check that the theta equals 1 positions are equal to R diag, so that's a substring. These ones here. And to decrypt, okay, so that's for the deletion. Of course, we want it to be an encryption scheme, so never mind the deletion, suppose that never happens. Suppose we wanted to decrypt using the key theta, so that would be the actual key theta. We'll simply measure all the qubits in the position theta equal to 0, and that will give us our comp, and that's going to be used as the one-time pad key to decrypt the message, because we already have M XOR our comp. Any questions about the scheme? The proof intuition. So this goes back to the uncertainty relations. Suppose you have an adversary and you're kind of looking at different attacks that the adversary could do. Like, you know, you could try to do certain things like partially measure, or you could try to maybe keep some side information. But our idea is that you need to produce this R diag substring correctly in order to convince Alice that the string has been deleted. So as that probability increases, you'd be forced to also measure the other qubits in also that same basis, because the adversary doesn't know which ones are the R diag and which ones are the R comp. She doesn't know the original encoding basis. So if you want to be really good at making the proof of deletion accept, you should also measure the other qubits in the diagonal basis, and that's going to erase them. So these are these uncertainty relations, I mean, just kind of informally, that the uncertainty in X and the uncertainty in Z are related as 1 over C, where C is the inner product or the overlap between the bases. That's kind of informally to understand why this should maybe work. So, yeah. Sorry?
What was C again?
Okay, so one of these, let's say this is the string. The measurement outcomes if you were to measure the entire string in the computational basis, and these are the ones if you were to measure the entire string in the diagonal basis.
What is C?
Oh, C, sorry, I heard Z. That's why we called it Z, C is the overlap between here it's 1 over square root 2, or 1 over 2, 1 over 2. So it's like the overlap between like the complementary bases. Okay, so coming up with the security definition, one of the important points of actually going towards proving security, we have like this combination of a game where it combines semantic security, which is about, or indistinguishability, which is about distinguishing underlying plain texts, with the certified deletion. So we'll have a game and here I combine it with the actual scheme. I mean, like formally you would want to separate these two things. I'll do the two at the same time. So we have this encryption key, a bit, oops, it starts here actually. The adversary creates a message. Alice will encrypt it using her key, and she randomly chooses, according to bit B, to encrypt the actual message or to encrypt the constant 0 message. Then she sends the encryption, the quantum encryption, which is this encoding, to the adversary. Then the adversary creates a string Y. In the honest case, this would be the proof of deletion. In the dishonest case, it can come from any type of process, quantum process that the adversary does here. And then Alice will accept if and only if Y is consistent with this R diag. And then the key is revealed, that's theta. And the adversary outputs a bit B prime. And we'll want to say that the adversary wins if we can bound the probability to be negligibly close to a half. A half, of course, being a random guess of what's the bit B. We'll accept if and only if this proof of deletion accepts and the bit B prime has correctly predicted the bit B. This is the choice, the random choice here. So this corresponds to security. Let's say it's exactly a half. That would mean that there's no advantage in the adversary in randomly guessing. If we completely break the scheme, it means that the adversary can know which one was encrypted, 0 or the actual message, while also having the proof of deletion accepted. And that would be bad, right? So that's what we want to avoid and prove that does not happen. And here's where this presentation could have taken a completely different path. So originally, yeah. Yep.
I mean, doesn't this allow the possibility that the attacker always gets a B, but makes the unparty accepted probability half?
Always guesses B correctly, and then it's the accept probability that will get this a half?
Yeah.
I think you're right. I don't know, the conditions are always a problem. I don't remember if we ended up, actually there was a modification at some point. I don't remember if this ended up being the actual definition or if this was an intermediate one, then we changed it. Yeah, so we should be careful that maybe, it's just pointed out that maybe there's something wrong here that this probability could be a half, and that's not what we care about. It's really this probability being a half, conditioned on accepting. I'll have to double check that. Yeah. Yeah, so as I was saying, this presentation could take a completely different turn depending on what proof technique we wanted to use to prove security. Here we used the entropic uncertainty relations that I alluded to previously in terms of a proof of quantum key distribution. So I don't think it's worth going into details about this at all. It would be possible to use a different proof based on sampling, and actually this was done in a recent work by Dakshita Kurana, who's going to be talking later this week. The point is that we're able to use the sophisticated techniques of quantum key distribution to have a noise tolerant, finite key analysis. The protocol is also prepare and measure a single qubit, and we get this certified deletion property. So when we also use privacy amplification, et cetera, which are all kind of the same techniques of QKD. And actually, that's kind of common in this area. If you're looking at your candidate protocol, to kind of wonder how could you map it to QKD? What's the relationship? What versions of QKD? And that could give you an idea of what proof techniques to start to work on. And I think, oh yeah, and there's some follow-up work with composability and different properties of to make like all of kind of, I guess is kind of this quest to make as much as possible of conventional cryptography to make it also certified, with certified deletion, let's say. So I think that's where I would like to stop right now. So I'd like to thank you and looking forward to your comments and questions.